Welcome to 5.6. This is about exponents and the scientific notation. So, exponential properties are very important because when you're looking at problems like, for example, 2 to the third power, and then you have another one, let's say 2 to the fourth power. And I wanted to know, is there an easy way for me to, let's say, multiply these two? These were situations that the properties of exponents might come in handy. You can then, when you learn the rule, be able to make this into a simple solution without having to figure out what 2 to the third power is immediately and what 2 to the fourth power is immediately, etc. Okay, and this is also useful in upper level math, in many different areas of science and all that, especially chemistry. When you're doing moles and all that, I don't know if you noticed, but there's a lot of scientific notation and exponents involved. So let's talk about the properties. Okay, these are the couple of properties that they expect you guys to know. The first property is called the product rule for exponents, and the product rule says the following. Remember, this is important. If you're multiplying, like the one I gave earlier, two different exponential expressions with the same base, I mean, that's very important. They have to have the same base in common. Then the idea is, well, I can make this into a single exponential expression, and all I gotta do is just add the exponents. Now I'm going to demonstrate to you why that's true. Okay, a moment ago I put 2 to the third power times 2 to the fourth power. Okay, and I said to you that this equals to, well, according to the rule, 2 to the 3 plus 4 power, which is 7, right? So this is what we should have gotten. But how do you prove that? Well, let's find out. What's 2 to the 7th power? Isn't it the same thing as saying 2 times 2 times 2 times 2 times 2 times 2 times 2? 7 of those? Well, what is 2 to the third power? Isn't that 2 times 2 times 2? What's 2 to the fourth power? 2 times 2 times 2 times 2. So if I were to multiply 3 2's and 4 2's, how many 2's are being multiplied? 7. 7 2's are being multiplied. So that's the idea. You're just basically counting how many 2's are being multiplied. But this is why it's important that the bases have to be the same. Because if suppose I gave you 2 to the third power times 3 to the fourth power, there you can't do anything. Because what do you have here? You have 3 2's and 4 3's. You really can't make this into a single 2 or a single 3. So in other words, you're stuck figuring out what is 2 to the third power, what is 3 to the fourth power. Once you get those two numbers, you can then multiply those two different numbers. So remember, they have to have the same base. Another important property is called the zero exponent rule. The zero exponent rule just simply states, as a definition, any base raised to the 0 power is always equal to 1 except for 0. 0 to the 0, I guess, is 0. So it's not equal to 1. Because 0 to any power is usually 0 squared is 0, 0 to the third power is 0. So the only exception is 0. 0 is that weird one. But any other base, so for example, 2 to the 0 power, that's 1. Okay, how about 12 to the 0 power? Still 1. Okay. So that's like a definition. How about 3, the power rule? The power rule is a situation where you have one base, one exponential expression, but you have two exponents. It looks like this. You ready? So 2 to the power of 3, all of that to the fourth power. That's where you have a situation where you have to use the power rule. Because now you have two exponents but one base. So what's the trick? Well, the trick is, according to the rule, is you just multiply the exponents. 3 times 4. So 3 times 4 we know is 12. But why does this work? Well, let's find out. What does this mean, 2 to the third power to the fourth power? Let's see what it means. It means 2 to the third power means 2 times 2 times... Actually, wait, before I go further, what's the 2 to the third power to the fourth power means? It means you have 4 2 to the third powers. That's a better way of looking at it. And you can use a rule we just learned a moment ago, right? You can just now add 3 plus 3 plus 3 plus 3 4 times. That's the same thing as 12. Or if you want me to break it down, 2, 2, 2 times 2, 2, 2 times 2, you're going to have 12 twos. So that's the demonstration. There's now another one called the negative exponent rule. Negative exponent is an interesting one because a negative exponent to an exponential doesn't make it negative. It's understood to mean it's supposed to be a reciprocal. So negative exponents mean reciprocal. Reciprocal means that it's going to change from one side of the fraction to the other. So for example, if you saw 2 to the negative 2 power, well, the fact that it's negative means it belongs in the denominator. Because right now, 2 to the negative 2 power is seemingly in the numerator. So it moves down there, and when it moves to the denominator, now it's positive. Exponentials turn positive when they go to the right location. So in this case, since I moved the 2 to the denominator where it belongs, now it's positive 2. And then of course, what's 2 squared? 4. But let me give you another example to clarify, because only the thing with the exponent that's negative is moving. Suppose I saw 3 times 2 to the negative 2 power. Well, this is another example. Let me just kind of block it off. Well, 3 doesn't have a... Let's put 3 squared. Okay? 3 has a positive exponent. So 3 stays on top. But 2 is the negative exponent, so 2 has to migrate to the bottom. So that negative exponent now becomes positive. And then we're ready to just do the squaring. So that's a 9 over 4. Just like that. So the negative exponent just means it belongs to the other side of the fraction. What happens if you have the negative exponent in the denominator? What if you saw something like this? 3 over 2 to the negative 2. That means that that negative exponent down there is telling you that 2 to the negative 2 power doesn't belong in the denominator. In fact, it's going to move up. It's going to become 2 to the positive 2 as a numerator. You're like, oh, what happened to the denominator? Well, when it's nothing there, we just ignore it. Yeah, and technically it's a 1, but we're not worried about that. So 3 times 2 squared, which is 4, and that gives us 12. Okay? So I'll make sure we understand these little examples, little demonstrations. And last but not least, the quotient rule for exponents. This one is telling you that if you are dividing exponentials and they have the same base, then you can simply do the shortcut. The shortcut is just subtract the exponents. Okay? Here's a quick example. 2 to the 5th power divided by 2 to the 2nd power. I can just simply subtract 5 minus 2 and get 2 to the 3rd power. I'll demonstrate it. The 2 to the 5th power means 2 times 2 times 2 times 2 times 5 2s. 2 to the 2nd power means there's 2 of them down there. Every pair factor cancels out. How many have left? We have 3 2s left. It's just that simple. What if it was backwards? What if you saw something like this? Let's put 3 to the 2nd power over 3 to the 5th power. Well, it would be 3 to the 2 minus 5, right? If you did it the way that they showed you, which is 3 to the negative 3. But negative exponents mean it's on the wrong side of the fraction, so it's really 1 over 3 cubed. But you can see this as obvious when you do it this way. 3 squared is 3 times 3. 3 to the 5th power. You have 5 3s. Every pair of factors cancel out. And there's nothing left on top. We're just going to call it a 1. We have 1 over 3 to the 3rd power. Which is what we found a second ago, okay? Oh my gosh. Perfect. Alright. So those are all the properties that you have to be familiar with. And there's going to be a couple of examples here. Now, I guess they're only using one property, the zero exponent rule. So remember, anything to the 0 power equals to 1. 1. This is an interesting one, because look at the difference between C and D. C is saying negative 14 to the 0 power, but D is saying negative times 14 to the 0 power. That's how you have to read it. So 14 to the 0 power is 1, but there's a negative in front of it. That's why it's negative 1 for D. So let's make sure we get that right. So for example, 1, 3 to 0, it's just simply 1. Negative 3 to the 0, that's also 1. But negative times 3 to the 0 is negative times 1, or negative 1. Alrighty. Alright, so now we're going to talk about scientific notation, okay? And of course, decimal notation. Decimal notation is literally just a decimal, okay? Whatever decimal you have, you just have it in a decimal form. But scientific notation attempts to make very, 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 very small or very, 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 very large numbers to fit in a single page. For example, if I ask you to put 1 and a million zeros, okay, you're going to be there all day. 1, 2, 3, 4, 5, 6. You're going to be there forever, right? That's a lot of zeros. Or you can say 1 times 10, and then of course you want a million, right? So you put a million. 1, 2, 3. There you go. And that means 1 with a million zeros. That's what that means. So you can represent such a giant number in a very condensed form. That's a huge benefit to scientific notation, which is why it's used in chemistry and particle physics and those kind of things. When you're talking about microscopic stuff, and it's used in astronomy, cosmology. Astrology is not a thing. So cosmology, astronomy, where they use giant numbers, right? How far is it from here into whatever planets? It's really far away. So they have scientific notations to represent giant numbers, etc. So anyhow, so here we go. We know what a scientific notation is for. Now, how do we go from, this is the first step, okay? How do we go from scientific notation to its decimal form, right? Its decimal notation. And it's actually quite simple. Check this out. If you have a scientific notation, this is what scientific notation looks like. You're going to have some number, actually they wrote it here. They're going to have some number, we'll call it A, whatever, lowercase a. And it's going to say times 10, and it's going to have a number and the power of 10. If the n is positive, if you have a positive n, that means it's a very, very large. You know what? Let me show you through example. I'd rather do examples. I don't like this variable. So let's say you have 2.5 times 10 to the 4th power, positive number. What this means is you're going to move the decimal 4 times, and since it's positive, to the right. So it used to be 2.5, but now look what I'm going to do. I'm going to take this decimal, move it 4 times. 1, 4 spaces. 2, 3, 4. And now it stops. You say, well, yeah, but there's a bunch of missing numbers there. You replace them with fillers, which are 0. So 2.5 times 10 to the 4th power is actually 25,000. That's another way of saying 25,000. What if it was negative? What if it was 2.5 times 10 to the negative 4th power? Okay, the negative means you're going to move the decimal to the left 4 times. So, if it was 2.5, I'm going to move the decimal left 4 times. 1, 2, 3, 4. It stops there, and I fill in the empty spaces with zeros. So 2.5 times 10 to the negative 4th power is just 0.00025. It's a very small number. So we're going to go ahead and do that for these examples here. Now I know they did A and B for us, but we're going to do it anyways. Since 7.4 is being multiplied by 10 to the 9th power, that means we're going to move that decimal 9 times to the right because it's a positive 9. So think of 7.4, and then let's just move that decimal. 1, 2, 3, 4, 5, 6, 7, 8, 9. So we're going to have 1, 2, 3, 4, 5, 6, 7, 8 extra zeros missing there. So we put a comma between every 3, right? We get 7,400,000,000. And that's it. That's A. What about for B? Same idea. Okay. We're going to take the decimal, 3.017, and we're going to move the decimal to the left 6 times. So 1, 2, 3, 4, 5, 6. We add zeros in its missing empty spots, and we're done. And so there's the answer. It's quite simple. One thing I forgot to mention, for a scientific notation value to be a good scientific notation value, the number that you have here before you put times 10 to the whatever power should be a number between 1 and 10, but it can't equal to 10. It has to be less than 10, but bigger than 1. Or it can be equal to 1, actually. It can be bigger than equal to 1, but it has to be less than 10. That's very important. All right, let's look at number 1. We have to do this one. So we're going to take 8 times 10 to the 7th. That means we're going to move the decimal 7 times to the right since it's positive. So, where's the decimal? Decimal is right there, right after the 8. So we're going to move it 7 times. Ready? 1, 2, 3, 4, 5, 6, 7. We put 0, 0, 0, 0, 0, 0, 0. 1, 2, 3, comma, 1, 2, 3, comma. So it's 80 million. Now we're going to do 7.86 times 10 to the negative 4th power. We're going to go to the left, since it's negative, 4 times. So 7.86, we're going to go 1, 2, 3, 4. We're going to have 3 extra zeros involved. So the answer is going to be 0.000786. That's it. It's quite simple. Alrighty. Now, what if I give you a decimal, and I just give you the original number, and I want you to turn it into a scientific notation? So I mentioned to you earlier that scientific notation has a number times 10 to the some exponent power. The number that it's before the times 10 part has to be between 1 and 10. It's actually right here. It's stated right there. So the idea is, so suppose you have a giant number like, I don't know, like 5 to, there you go, 5,200,000,000. And I know the decimal is located right there. I'm going to see how many times do I have to move this decimal so that the number that I have is a number between 1 and 10. Let's see. If I move it once, 2, 3 times, it's still too big. That's 5 million, right? 3 more times, it's 5,000, too big. 2 more times, it's still 52. 1 more time, if I leave it there, now it says 5.2. That's what I want. I want to get 5.2, and then I have to ask myself, how many times did I have to move that decimal? So 5.2 times 10, they always put this, scientific notation always carries that times 10 to the power of. Now the power I put there is the number it takes for the number of moves I used to get to reach to that point. So I had to move the decimal 1, 2, 3, 4, 5, 6, 7, 8. I had to move it 9 times, so I put it 9. And you're thinking, well, should it be positive or negative? If you want to go back to its original value, what direction should that decimal move? Left or right? Well, it needs to go to the right to go back to its original, so that has to be a positive 9. Okay? Suppose you saw something like this, 0.00000045. Okay, how do I do that? Simple. You move the decimal until you get a number. 1, 2, 3, 4, 5, 6. Still not enough. Even though I moved this 6, it's 0.45. You have to get past 1. So 1, 2, 3, 4, 5, 6. We need one more. 7 times to get 4.5. So 4.5 times 10. Now I know 7 goes here, but is it positive or negative? Well, it's going to be negative this time. Why? Because if I want 4.5 to go back to its original, I need that decimal moving left. That's why I make it negative. And voila. That's how you do it. It's pretty straightforward, pretty simple. Let's go ahead and see that what they did here for letter A. They had to move the decimal 1, 2, 3, 4, 5, 6, 7. They couldn't stop there. It's too big. 741 is too big. 8 is too big. 774.1 is too big. 9. They have to move it 9 times to get 7.41, which is now between 1 and 10. And of course, if you want to go back to its original, you need to move to the right which is why it's positive 9. And then for B, they went ahead and did the same thing. They moved the decimal. They moved the decimal. See how many times I got to move it. 1, 2, 3, 4, 5, 6, 7. 7 is not enough because it's 0.92. That's not bigger than 1. So you have to move it 8 times. That's where the 8 came from. Now, why is it negative? Because if you want to go from 9.2 back to its original, you got to move it left, so you make it negative 8. And that's simple as that. Let's try these two now. So you have 220 million. The decimal is here. I want to make this into a scientific notation, right? So 220 million. The decimal there. I'm going to move it until I reach to a number between 1 and 10. 1, 2, 3, 4, 5, 6. Now I got 220. It's too big still. 7. It's still too big. That's 22. Boom. At 8, you get 2.2. Now, is that going to be a positive or negative 8? Hope you're thinking it's positive because, again, if I want to move 2.2 back to its original 220 million, I have to move the decimal to the right. And last but not least, 0.000000293. I'm going to go see and count how many times I have to move that decimal before I get a number that's between 1 and 10. Let's see. 1, 2, 3, 4, 5. Not enough. 6. I'm going to get 2.93. And now I'm going to multiply that by 10. That's part of the scientific notation. And ask myself, how many times did I move that decimal to reach that? It was 1, 2, 3, 4, 5, 6. It was 6 times. But if I want to go back to its original, I have to make it negative, so that way it can move to the left. Okay? And that's how you do scientific notation. So if you have the decimal and you want to write it into scientific notation, that's the way to go. Alrighty. Another objective. So this is important, especially if you're going to take chemistry or anything like that, because you're going to work with a bunch of scientific notations. So you're going to go ahead and you're going to be able to multiply or even divide two different types of scientific notations, two numbers in scientific notation format, without actually having to convert the scientific notation to the decimal form. A lot of people think, oh, if I want to simplify scientific notation, multiply by another scientific notation, that's going to require me to evaluate each scientific notation to decimal form and then multiply the decimals. No. You can leave it as scientific notations. Okay, I'm actually just going to go straight to the guided example. Oh, they only have multiplying. I might show you dividing. Yeah, I'll just show you dividing. So this is how it works. The way you're going to do it, if you're going to multiply two different scientific notations, it's quite simple. The part with the scientific notation, the 10 to the 7 and the 10 to the negative 2, they're going to go together. Excuse me. And the part without scientific notation, which is 1.3 and 4, they're going to go together. So you can think of it as 1.3 times 4, right? They merge into 1.3 times 4. And then the 10s merge into 10 to the 7th times 10 to the negative 2. And you're going to still multiply them, okay? But now you can just sit there and do them separately. What is 1.3 times 4? This is 5.2. How do you multiply 10 to the 7 times 10 to the negative 2? Well, we learned this as a property of exponents. We just add the powers. 7 plus negative 2, that's just 5. So it's times 10 to the 5th power. And voila. You got your answer. So you can do that for scientific notation. And then it says, oh wow, then it says write in decimal. Okay, so that last part is silly, but the main thing is to convert it to that. If you want to convert that to decimal notation, that means move 5 times to the right. So 1, 2, 3, 4, 5, and you're going to get that number. Okay? Let's see. Yep, they ask you to do the same thing. They want you to do it. Once you figure out what the answer is, they want you to write it in decimal notation. We'll go ahead and do that. But let's remind ourselves, the 2 and the 3, they multiply together, okay, because those two are not part of the 10s. And the 10 to the 9 and 10 to the negative 5, they go together, because they're part of the 10s. And they're still all multiplying. Now 2 times 3 is obviously 6. And 10 to the 9th times 10 to the negative 5th. The property says you just add the powers. 9 plus negative 5 is 4. And then we're going to go ahead and evaluate that. That's 6 times 10 to the 4th. That means you're going to move the decimal to the right 4 times. So 6 has a decimal right there. 1, 2, 3, 4. So we're going to add those zeros. So the answer is 60,000. Now I know it's not on here, but I'm going to show you dividing, a division one, a dividing one. Suppose you saw this. 3 times 10 to the, 7th power divided by 2 times 10 to the 3rd power. How do you do this? Well, it's actually pretty easy. What you're going to do is you're going to split this into, you're going to think of it as two things. You're going to think of it as 3 over 2 times, and then you're going to put 7 over 10 to the 3rd. Basically, you split it like that. Like you split the part with tens and the part without the tens, and now you have basically two fractions. The next step is to convert this fraction to a decimal. So use your calculator. 3 divided by 2 is 1.5. We're done with that one. Times, and then what's the property for quotients? Well, we don't add the powers, we subtract them. So 7 minus 3, 4. And voila. That's the new scientific number. Pretty simple. So now we're moving on to the next objective. So this is going to be, okay, I don't think this is tested, but this is just going to be problems where you're going to have to, okay, well there it is, the division, okay. So they're going to give you a question where they're going to ask you to divide, and which is fine. So if you were to divide these two different scientific notation values, again I told you, you take this and you divide it separately. That's what they did here. And you take the tens and you divide them separately. Remember the rule for the 10 to the 10 divided by 10 to the 5th. All I gotta do is subtract the exponents. So 10 minus 5 is 5, and 4.08 divided by 6.8 is 0.6. And then they ask you to turn it to a decimal, so you move the decimal 5 times to the right, and that's how they got the answer of 60,000. So it's just simple math. Let's look at this one here. There are 3 questions, and that's the last part. So let's see if we answer them quickly. The bar graph shows the total amount of Americans paid in federal taxes in trillions of dollars and the U.S. population in millions from 2012 through 2015. Use these numbers to answer the question. In 2015, the U.S. government collected 3.18 trillion in taxes. Express this number as a scientific notation. So, trillion basically has a lot of zeros, right? So it's 3, 180 billion, 000 million, $1,000, like that. So that's 3 trillion. So let's see, that's going to be 3.18 times 10. Now we're going to move the decimal how many times? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Wow, that's a lot. That's a whole lot. So it's 12 times we have to move that decimal. So there you go, 3.18 times 10 to the 12th power. That's for number 1, okay? I'll just do that. All right, number 2. In 2015, the population of the United States was approximately 320 million. Express this as a scientific notation. Okay, so 320 million $1,000, or not dollar, but ones. Okay, so I'm going to move the decimal. It's here. 1, 2, 3, 4, 5, 6, 7, 8 times to get to 3.2 times 10 to the 8, and I want to move it to the right 8 because I want to go back to where it used to be. There it is. The solution for that one is 3.2 times 10 to the 8. And then the last question is use the answers from part 1 and 2 to answer the question: if the 2015 taxes were collected evenly amongst all Americans, how much would each citizen pay? Okay, so we take the total amount of money collected divided by how many people we collected it from, right? And then we figure out what that equals to. Now remember, the 3, this is going to be divided separately, and then these 2 are going to be divided separately. Now remember, to do the tens, we don't really divide, we just subtract the powers. So I am going to use my calculator to figure out what is 3, here we go, 3.18 divided by 3.2. So in my calculator, this gave me 0.99375. Let me double check that just to make sure. 3.18 divided by 3.2. Yep. 99. Okay. And then 10 to the 12 times divided by 10 to the 8. We just subtract the 2 powers. We're going to move that 12 minus 8 will become a positive 4. And now we're going to move the decimal 4 times to the right. So 1, 2, 3, 4. So it's 9937.5. That's how much. So basically almost $10,000 in taxes from each person. So I hope that made sense. And I believe that's it for the lesson. Yep, we're done. So if you have any questions, guys, and by the way, these notes also include all the answers that when we went over it. So if you guys want to, do it on your own and see how how you would do it, whatever, go ahead and do it on your own, and then check your answers. You can always go back and see how I did mine, and then that's it, and you'll be fine. So alrighty, guys, well, have a wonderful day, and we'll see you guys for the next lesson. Take care.